Right, wonderful people. Let us now look at elastic and inelastic collisions in grade 12. Now, there's a reading that I want to break down for you in this book. It says all collisions in an isolated system, that is a closed system, that is a system that has no external forces acting inside of it, conserve momentum. So these systems conserve momentum, so meaning momentum before and after remains the same. However, the kinetic energy is only conserved in certain collisions. So not in all collisions you can have kinetic energy being conserved. It depends on the situation of interest. In these collisions, no energy is transferred as sound, heat, or any other form of energy. We say that a collision is elastic if kinetic energy is conserved. So kinetic energy before, if it is the same as the kinetic energy after the collision, therefore the system is an elastic collision. The collision is elastic. This means that the total kinetic energy before the collision is equal to the total kinetic energy after the collision. Right, let us look at the mathematical description or formula that governs what we have just read. Now, you would know that kinetic energy is equals to half mv squared. That is the formula for kinetic energy. So kinetic energy is equals to this, but remember there is a change because we are speaking in terms of momentum before and after. So we would say, okay, this would be half m, let's say m1 vi 1 squared plus half m2 v I2 squared. This must be equals to half m1 vf1 squared plus half m1 vf2 squared. So that would be the formula for kinetic energy in terms of momentum. So kinetic energy before must be equals to the kinetic energy after, and if before is equals to after, then we know this is an elastic collision because kinetic energy is conserved. But remember, not in every system, it is dependent on whatever the conditions may be. We say that a collision is inelastic if the total kinetic energy before the explosion is not equals to the total kinetic energy after the explosion. Now remember what we said. We said all collisions in an isolated system conserve momentum, but not necessarily the kinetic energy. This is very, very important. It doesn't necessarily mean if you have an isolated system where momentum is conserved, automatically you will have kinetic energy also being conserved. It is very much dependent. It is very much dependent on what we will see as time progresses. For two blocks colliding inelastically, we know if that is an inelastic where the kinetic energy is not conserved, kinetic energy before is not equals to kinetic energy after. What is it that we know? We know that half m1 vi1 squared plus half m2 vi2 squared is not equals to half m1 vf1 squared plus half m2 vf2 squared. This is something that we know. Right. To determine whether a collision is elastic or inelastic, we compare the total kinetic energy before and before the collision to the total kinetic energy after the collision to establish whether they are equal. Right. Let us look at one example where this mathematical description and formula can be applied. They say to us now, determine whether the collision between the two colliding cars in the previous example is elastic or inelastic. So meaning, what is it that we want to check in here? We want to check whether this explosion is this elastic or inelastic. This is what we want to check. So the first thing that we will do obviously is introduce the formula, and then after introducing the formula, plug in the values of interest. So I'm going to calculate kinetic energy before. Now remember, the data is there and it is provided for us. So I know kinetic energy before, that would be half m1 vi1 squared plus half m2 vi2 squared. So let me find what the value would be here. So m1, let's start first with car A, and let's say the mass is 600, the initial is 28. Remember, velocity must be squared. Very, very important. Half mv squared, right, plus half the second mass would be 900. What was the initial velocity? 16, that is squared. Now let us see what we will find from this. Right, let me just come here and say half is the same as 0.5 being multiplied by 600 being multiplied by 28 squared. I get 235,200. Now remember, this is energy, so this would be joules of energy before the explosion, right? And then let's try to find kinetic energy after. And we would find half m1 vf1 squared half m2 vf2 squared. Half, we said 1 would be 600. What was the final velocity? That's what we calculated and found it to be 16. But where was that? In the west, and we took west as being positive, remember. So that would be positive 16, that is squared 1/2 900. The final velocity was provided to us also in the west as 24 squared. Now let's try to see what really transpires in here. So 0.5 will be multiplied by 600 and will be multiplied by 16, that is squared, and I get 78,800. Okay, let me just insert this entirely, because let me just go to the first one. Let me just check if I did not make any mistakes. Sorry, 0.5 times 600 times 28. Sorry. Okay, 0.5 times 600 times 28 squared plus 0.5 times 900 times 16 squared. No, there's a mistake here. There's a mistake. This was only for this. I'm sorry, but for both this is not the answer. The answer is 350,400 joules. Please forgive me for that mistake. I only calculated for this, I did not incorporate that. I'm very sorry for that. Now let's go to the second one. We have 0.5 by 600 by 16 squared plus 0.5 by 900 by 24 squared, and I find 336,000 joules. Alright, now let us try to look into this. Now, even though this system is an isolated system, we saw that momentum before is equals to the momentum after. Did we try to prove that? I'm not sure here. I'm not so sure whether momentum was conserved or not. We were not interested in that. I'm not very sure whether we checked whether momentum was conserved or not. We just calculated the velocity. But if it is conserved in here, which is just an assumption, look at what I get here. What does this tell you? Kinetic energy before is not equals to kinetic energy after, so this will be an inelastic collision. So even if momentum is conserved but kinetic energy is not conserved, so this is an example of an inelastic collision, right? That is fine. Let's go to another example. So please go and try check for me whether momentum is conserved or not, so that you can conclude in here in the right way of concluding. It is your responsibility to go and do that, right? Let me just draw up a line, and in this line we're going to deal with another problem. They say to us in here, an astronaut of mass 75 kilogram carries a pack of mass 25 kilogram. He accidentally separates from his spacecraft and floats in space for a distance of 15 meters from the craft. The astronaut knows that the only way to get back to the spacecraft is to push away his back. Obviously, this is Newton's third law of motion. If he pushes away the back, he will be pushed with equal but opposite force, and therefore he will be propelled back into the craft. This is just basic physics, right? The astronaut knows that the only way to get back to the spacecraft is to push away his pack. Determine the direction and velocity relative to the spacecraft that the astronaut must push away his pack in order to return to the spacecraft in 30 seconds. Now let us try to read and make sense of this. An astronaut of mass 75 kilogram carries a pack of mass 25 kilograms. So we can have the total mass before as 75 and 25. That is fine. He accidentally separates from his pack. That is after the collision, one would say. He accidentally separates from his spacecraft and floats in space for a distance of 15 meters. So we have the distance, which is 15 meters. That is fine. The astronaut knows that the only way to get back to the spacecraft is to push away his pack. Determine the direction and the velocity relative to the spacecraft that the astronaut must push away his pack in order to return to the spacecraft in 30 seconds. So time is 30 seconds. What is it that they want? Determine the direction and the velocity. So velocity is unknown. Now the question is, how do we solve such a problem? Now we have a distance, we have time, we are looking for velocity, a triangle known as the triangle of let me not go there. We know know that speed equals distance over time. This is what we know. Speed equals distance over time. Therefore, distance is equals to speed multiplied by time. The triangle of speed, distance, and time relationships. So I can use this in order to find that which is required. So they are looking for velocity, which is the same as speed. So this is distance over time. What is the distance? 15 meter. What is the time? 30 seconds. So the speed will be 0.5 meter per second. So that would be the speed. Now, and they said the direction. Right. Determine the direction and the velocity relative to the spacecraft that the astronaut must push away his pack in order to return to the space craft in 30 seconds. So what will we say is the direction now? Huh? What will be the direction now? This is the question. So how do we solve this? How do we solve this? Now, what is this velocity that we have found? What is this velocity? Because they said determine the direction and the velocity relative to the spacecraft that the astronaut must push away his pack in order to return to the spacecraft in 30 seconds. That is the question. Right. Remember what we were provided with before. Okay, we have the distance and we have the time. That is fine. We find this is speed. So this is the speed. If this is the speed that he will move if this distance is provided at that time. Okay. Now, the question is, if the astronaut pushes the backpack away, is momentum conserved or is it not? Because let's read this. Determine the velocity and the direction relative to the spacecraft that the astronaut must push away his backpack in order to return to the spacecraft in 30 seconds. When he is pushing away this space pack, whatever the bag that he has, when he pushes away this backpack, well, is momentum conserved or not? This is the question that we need to ask ourselves. Is the momentum conserved or not? Right. One thing that we can look at, because remember what they said. The question said, determine the direction and the velocity. We have the speed here. The speed, which is the same as the velocity, because somebody might say that velocity is equals to the change in displacement over the change in time, which can also give you the very same thing. 15 meter by 30 sec will give you also that 0.5 meters per second. So velocity and speed is the same here. Velocity is your speed because the speed is in a certain direction, and velocity also, they are both vectors and are measured depending on whether the displacement it's in kilograms, meters, and so on and so on. So whether you use this or that, the answer will be the same. Right. Now, they said determine the direction and the velocity relative to the spacecraft that the astronaut must push away. So we are saying when he pushes away the backpack, is momentum conserved or not? Now, we are going to treat this as a collision because he accidentally loses the backpack. So we're going to say m1 vi1 plus m2 vi2 equals m1 vf1 plus m2 vf2. But we know that initially the astronaut and the backpack as a unit have the same velocity. So I'm going to say m1 plus m2 vi, and then here I know when they separate they are moving at different velocities, so I'm going to treat this more like an explosion. Right, and then from there I'm going to have my m1 vf1 and my m2 vf2. So right, now in here, what is it that I have? I have the mass of the astronaut plus the mass of the backpack, which is 75 plus 25. And then what is their velocity? Remember, initially they are both at rest, so meaning their velocities is 0. And why are we sure of this? Let's read back. An astronaut of mass 75 carries a backpack of mass 25. He accidentally separates, you see, so they were not moving before the separation, therefore their initial velocity is 0. So here I will have 75 times now the velocity. Now remember, this is the velocity of the astronaut, so this is, and then now here comes something very, very important. The direction here. How do we determine the direction? Now, if we take the motion towards the spacecraft as positive, towards the spacecraft, so this is going to be positive. Let's take the direction towards the spacecraft to be positive. Remember, this is the velocity towards the spacecraft, so we're going to have this as positive. And then we're going to have 25. Now I'm looking for the velocity of the back, because they said determine the direction and the velocity relative to the spacecraft that the astronaut must push away his backpack in order to return. So what am I calculating in here? I'm just calculating the velocity of the pack. If you have to move away with this velocity, what is the velocity of this the backpack as it is moving in the opposite direction? Because you are pushing it away, as a result you are being propelled towards the spacecraft, whereas the backpack is moving away from the spacecraft. Therefore we want to find that velocity when they separate, because their velocities are different. So if this is 0, the whole thing is 0. So I'm going to have let me just check. I am just going to have 75 by 0.5. So this is 1/2, and that should give you 37.5. 37.5. Remember, kilogram meters per second plus 25 vf2. So this is something that we have. Right, I can take this to the other side. Negative 37.5 kilogram meters per second, and we'll be left with 25 vf2. 25 vf2 would be, let's check. So I'm just going to divide an answer by 25. 1.5, so this would be negative 1.5 meters per second. So final velocity equals 1.5 meters per second in the opposite direction. In the opposite direction, or somebody can say away from the spacecraft or away from the astronaut. You can just see there are different ways in which you can state that. There are different ways in which you can state that. Right. Do we have another problem? Yes, we have number B. So number B is what now? Right. Is the collision between the astronaut and his backpack elastic or inelastic? Support your answer with relative calculations. So now they want to know whether the collision is elastic or inelastic. So half mv I squared m1 plus half m2 vi2 squared. Right, this is kinetic energy before. Let's find it. Half, let's take m1 as the mass of the astronaut with his initial velocity of 0.5 squared. This is 25. What is its initial velocity? Because this is something that we need to determine. Right, remember between the astronaut and his backpack. So we will have what is the velocity there? The question is, what will be the velocity there? Now, before the collision, right? Before the collision, right? The first thing that I think we should do before, what was the velocity? Now, let us look into this. Let us look into this. Now, before, remember what we said. If we are given the speed, in fact, if we calculate the speed, we are given the distance from the distance of the astronaut to the craft. The aircraft was 15. He needs to get in there in 30 seconds. We found the speed. This is the speed, right? And then in here we found the final velocity of the backpack. It has to be pushed and then it will go with a velocity of 1.5. Then that is fine. Now we are saying kinetic energy before it was being pushed. What was its velocity? 0. The velocity was 0 squared. Right, and then what is it that I can do? Now I can begin to calculate now. Right, what I can do there is the following. I can say, all right, let me just see the answer that I will get. Let me just say 0.5 by 75 by 0.5 squared, which will give me 9.375 joules. This is the kinetic energy before. Now let's look at EK after. Now let's see after. Half m1 vf1 squared plus half m2 vf2 squared. So half 75. What would be the final velocity now? Let us look into this. Let us look into this. Now, is this even making any sense? This is my question. Is this even making any sense? If I say the final velocity there is also 0.5, because I said initially it's 0.5. If I say finally, because I can't use this, I can't use this. This is the final velocity of the backpack. So meaning initially the astronaut and the bag, their velocities before, so meaning this is the final. Before, remember before, they were a unit. And what was their initial velocity? Their initial velocities was 0. So now let's go and correct this. What is this? This is 0. And it makes kinetic energy before as what? 0. This is very, very important that we make these mistakes so that you understand exactly what is happening here. Remember, before, the backpack and the astronaut have not yet separated, and remember we said in an explosion related content, we said that they are moving at the same initial velocity. And what was the velocity? 0 for both. Only after separation they are moving with different velocities. So meaning initially this is 0. Remember, what is this? This is the final velocity that the astronaut must have in order to get back to the aircraft. If the distance between him and the aircraft is 15 meters and the time required to get in is 30 seconds. Very important. So it is very important to see why we need to make those changes. So the final velocity, we will write that, meaning we will take the direction heading to the spacecraft as positive. So that would be 0.5 squared plus 1/2, which is 25. Now look at this velocity that we got. That was negative 1.5 squared. But this should just tell you by definition that this is an inelastic. Whatever value that you get there, this would be inelastic. Why? Because the kinetic energy before is not equal to the kinetic energy after, even though momentum is conserved. Remember, that is what we read. These are some of the things that are worthy of noting. In the first statement, they said an astronaut of mass 75 carries a backpack of 25. He accidentally separates from his spacecraft and floats in space for a distance of 15 meters from the craft. The astronaut knows that the only way to get back to the spacecraft is to push away his backpack. Determine the direction and the velocity relative to the spacecraft that the astronaut must push away his backpack in order to return to the craft in 30 seconds. And then what did we say? We said when the astronaut pushes the backpack away for himself, momentum is conserved. That's exactly what we said. That is exactly what we said. So even though momentum is conserved, kinetic energy is not conserved. And this is something very, very important that I wanted to share with you guys. Now that we are done with the principles of conservation of linear momentum, in the second tutorial we will look at impulse.